like nature's done something crazy, and it was like, what experiment has it performed, and what is it telling us about how the universe works?
You're listening to The Cosmic Cast. Hello, and welcome back to another episode of The Cosmic Cast. I'm John Penny-Fisher, and I'm joined with the usual co-hosts of Peter McArdle and Marissa Lowe.
Hello.
Hey.
And joining us this week is Oli Shorttle. I guess you're based at the University of Cambridge, is that right, I think?
Yeah, at Cambridge.
Excellent. So, yeah, Oli, we thought you'd get you on this week because I guess you've had a really fascinating sort of diverse range of things you've worked on over the past, I guess nearly 10 years, I guess almost. You've gone from isotope geochemistry to exoplanets. So maybe we give a bit of a rundown in terms of, how your career pathway has developed and how you've gone from like terrestrial geochemistry to thinking about objects outside of the solar system.
Yeah, so I think I came when I started my undergraduate, I really wanted to study space, and like I'd always been fascinated by space, astrophysics, black holes, galaxies, planets, and everything. And so I kind of was going everywhere to do a physics degree and then move into astro whenever I could. And then I started doing the physics degree, and I guess maybe I was just like super impatient and I don't know, a bit rubbish at physics or something. And it felt like a lot of what we kind of learning was really it felt disconnected from the opportunity to kind of immediately tackle like research questions. So I suppose I learned pretty quickly whilst I was super interested in space, I was kind of interested in being able to ask and answer questions. And so at the same time as doing physics, I was taking courses in earth sciences, and it felt like there was a lot earth scientists didn't know about, whereas physicists sounded like very certain about everything. So I suppose I was drawn to the kind of the gaps in knowledge that earth science appeared to offer, whether it be, about volcanic processes or, deep earth processes or whatever. So I ended up becoming a geologist or doing my earth science degree, and then doing my PhD. And I suppose I kind of, in the last year of my undergrad, sort of became more focused on like igneous petrology, kind of mantle melting, thermodynamics, and sort of how we can use magmas to sort of decode processes and stuff about the composition of the interior of Earth, like completely like terrestrially focused kind of research.
So I think we have that in common. I think we both worked in the northern rift zone of Iceland. I don't know if you remember a few VMSGs ago. I think we both presented on some very similar work once upon a time.
Yeah, I mean that's like a very niche connection. But that was like my PhD was like rooted in like a field area. Like not only was it terrestrial, geology, it was terrestrial geology like of a place, like of a place you could like specifically go to and collect rocks from. And so like trudging around that like beautiful, cold, windy and wet bit of northern Iceland was how I spent a decent portion of my PhD, which I was enormously lucky to be able to do. And I guess, so weirdly, I think without me knowing it at the time, I sort of, the kind of questions that I was beginning to ask of those magmas that I was collecting, we were looking at in northern Iceland, I sort of at some point realized that these were questions which were sort of a little bit more general than maybe specifically, a story about Iceland or the North Atlantic or even, how Earth is operating, but they kind of maybe speak to planetary processes kind of in a some more universal way. And I guess the aspects of the kind of questions we were trying to ask with those Icelandic lavas were things like, how much carbon is being stored inside the Earth, and how hot is the inside of the planet, and how is plate tectonics, how's the movement of plates on the surface of the Earth and then being kind of shoved back inside it at subduction zones, how has that been recorded in the magmas we see in Iceland? And so that was kind of beginning to touch on just sort of large scale kind of planetary processes. in a way that I think began to speak in a way more directly to questions we might ask in the abstract about exoplanets than it does more specifically to like solar system science. In a sense, you know, we know that aspects of what we learn about the interior of Earth through Iceland are not going to be relevant, or not, you know, not obviously relevant to some aspects of like Martian and Venusian geology, because of the very different histories of those planets. But it was, you know, open up the possibility that actually, you know, some exoplanets are perhaps, you know, could be in principle closer to that regime of operation, or there's some generalities that maybe speak to the kind of questions we might ask of exoplanets. So those general ideas of like a volatile cycling, I guess you might kind of pitch it, you know, those large scale processes by which planets put gases into their atmosphere and hide them again in their interior. That sort of general concept became a real kind of linking point between the questions I was asking in an Earth science context and the questions you might want to ask in an exoplanet context. And so sort of after my PhD, really kind of during my postdoc, and then starting back at Cambridge, sort of really began to explore those links more deeply.
So yeah, I can tell that you must have always had the brain of a researcher then, if you know, started on the path of physics and then thought, ooh, geology, we don't know what's going on as much there, and you decided to go that way. Was that, so did you start a physics degree, or were you able to do modules for both subjects?
Yeah, so I started doing natural sciences. So I'd done such a sort of a limited range of like A levels. I'd done like politics, maths, and physics. So I was sort of barely equipped to be a scientist at all. And so I couldn't do what, you know, most people would have done, which would be, you know, physics, chemistry, and then, you know, probably something quite a lot like physics or chemistry. Because I didn't know any chemistry, or I hadn't properly been taught chemistry since GCSE, then it's like, oh, I'll do Earth sciences. So it's sort of, it was sort of a welcoming home to people that had politics A levels. So it was a complete chance. But yeah, because I learned in that first year that it was, like you say, it was kind of research more than just learning about equations, you know, that some dead people figured out ages ago. That's what appealed to me. I needed the sort of reason, like, you know, I like equations, but I want to know why I'm using it. And I think Earth science gave that reason. It's like, you know, here's a problem, and, you know, let's go and solve it. And maybe we need to, you know, go and get cold in Northern Iceland to do that, and hit a thing like with a really big hammer. And maybe we also need to do some equations. And it was that kind of good combination of like walking, hammering, and equations that was sort of unique to Earth sciences.
Yeah, I guess we've said before on this show, I mean, I guess it's, you know, geology in some ways, it's the application of all these different sciences in many ways, isn't it? It is satisfying how tangible it is that you can pick up a rock and, you know, hold it in your hands and tell so much about, you know, the deep earth almost. And that to me never ceases to be amazing, really.
I think in the context of like the kind of questions we're really excited about now, in terms of, you know, like creating habitable planets and stuff like that, it really reaches across, you know, the core sciences of biology, chemistry, and physics. You know, you're sort of, I mean, I like the fact that in principle you might want to draw on any of those disciplines to answer the question, and that although, you know, I'm never going to be a proper physicist, a proper chemist, or a proper biologist, you know, you can sort of work with expertise from each of those fields and bring it together to help answer questions in the planetary sciences.
And hence why Earth sciences is the superior discipline, clearly.
I love it. We didn't even like bribe you to say this, Ollie, but that's a conclusion we've come to, so thank you. So perhaps to dive a bit into more what you did for your PhD then. So you said you were trudging around, hammering, collecting samples in Iceland. What were you looking at specifically?
I feel like it gets quite niche when I actually explain what I was trying to do for my PhD. Yeah, so I guess, yeah, just to kind of step back, like, Iceland is a lovely island sticking up in the air in the North Atlantic. I'm sure you've probably heard lots about Iceland before on this podcast, judging from some of the names that I have been on it before. But just to kind of ground what I'm going to say, so it's sticking up in the air, and it's obviously on the mid-Atlantic ridge. So it's anomalous in the sense that most of the tens of thousands of kilometers of the mid-Atlantic ridge are decent enough to stay below sea level, and it's peculiar that on Iceland it's raising its head above water, and so that obviously speaks to some anomaly, something weird happening inside the Earth at the location of Iceland, and that weirdness is a big upwelling of, or is in all likelihood a big upwelling of rock from deeper in the planet that's hot and kind of pushes up the surface of the Earth at that location. So, like, what my PhD was aiming towards was creating kind of a picture of the compositional structure of the mantle beneath Iceland. So it'd been known for a long time that the mantle is compositionally anomalous beneath Iceland, at least with respect to nearby mantle. And what we were doing in the northern rift zone of Iceland was kind of filling in a gap, essentially, in our picture of the composition of lavas erupting, and seeing whether some trends some spatial trends in how magma composition was changing as you moved northwards onto Iceland and across the island, whether that was sort of a continuous change or whether it was like a sudden sharp change. And so really the kind of heart of the problem was trying to get an understanding of on what length scales the interior of the planet is compositionally variable. And that comes back to really asking questions about what are the processes that create compositional variability inside planets, and how is that distributed and stretched and warped and maybe destroyed by mixing over time. And obviously the kind of underlying process that might create composition anomalies like that would be plate tectonics, possibly. And so, subduction zones putting things back inside the Earth. And that creates compositional anomalies we might detect hundreds of millions of years later as those mantle domains get picked up and melted beneath places like Iceland. But it could also be kind of more ancient compositional structure in the planet. So, structure that's left over from the planet's formation, even when it was molten and then cooled and crystallized as a one big giant kind of magma pool, magma ocean. There's the possibility for compositional structure having been created then that still to this day, billions of years later, hasn't been destroyed. So whilst my PhD was maybe to some extent agnostic about which of those processes or what combination of processes had created the compositional variability, we're interested in developing the tools to see it in the first place and map it and say something about what it means for spatial structure of compositional variability in the planet.
If we can access all this information about the Earth and all these sort of potential deep processes through the rock record that we have, how then have you found sort of transitioning to think about some of these questions in exoplanets, where obviously the amount of data we have is much less? I mean, that to me sounds like it'd be quite frustrating in many ways.
Yeah, I think it's frustrating or liberating depending on the perspective. So I definitely feel like it changes the sort of questions you're asking, I suppose. Like, so in the earth science context, like nature's done something crazy, and it was like, what experiment has it performed, and what is it telling us about how the universe works? For exoplanets, I think one day we'll be there, and that we'll be back in that situation of seeing a thing and scratching our heads. But I still think there's kind of useful work to do kind of in the meantime. And in the context of, I guess, my geological roots, which lies like in igneous petrology, thermodynamic modeling of melting high temperature processes, I think the translation has been from thinking about like the magma being the product of that theory, and me interrogating the petrology or crystal composition or whatever of a lava we can pick up, to thinking about, well, how are these processes influencing the atmosphere, and the atmosphere being the kind of medium through which we might learn anything about the planet. So that's been the kind of transition. And so for rocky exoplanets, we're not really even there yet in terms of having resolved atmospheric spectra that tell us about the average composition of the atmosphere, let alone any temporal variability. But we might be there for one or two objects in the next handful of years, and in the kind of next decade, 2 decades, that's where I guess we're shooting for with the observatories, ground-based and space-based. So what it's meant is, in terms of like kind of developing our research tools, it's kind of taking that kind of theoretical knowledge, which I guess is founded on experimental petrology that's happened with an eye to explaining terrestrial processes, and calibrated also by observation of terrestrial magmas, and thinking how does volcanism connect to planetary atmospheres, or how do planetary atmospheres tell us about geological processes on the planet? And one point of communication between the big lump of rock that is the planet and its tenuous atmosphere is volcanism. And I suppose that's the thing which is closest to my expertise, to the extent I have any expertise. But obviously it also raises a whole load of other possibilities, like obviously biology has something to say about atmospheres if it's present. But also, a whole host of low temperature geochemical processes as well, which has kind of led to me kind of getting interested in, silicate weathering and, the archive of silicate weathering processes on Earth, as part of Earth's regulation of its carbon cycle and its climate. So kind of turning everything around and just asking this question, what do atmospheres tell us about geology? If we had to infer all geological processes through stuff in the atmosphere, life would be really challenging, but what is that connection? And so, that's where that's the link back to the volcanoes, but also then a host of other processes, which has kind of been a sort of developing part of my kind of research and my collaborators' research over the last few years.
So what sort of data do we have about exoplanet atmospheres then? Is it a series of pictures? Do you get any sort of temporal variations, or do you just have like one data set to work from?
So yes, that's a really good question. And there's kind of not one answer to it. So I guess that the atmospheres that are best studied are like giant planet atmospheres. So that would be like Jupiter mass planets, and typically Jupiter mass planets that are on very short period orbits, so that have like a year that's maybe a handful of Earth days long, or even less than an Earth day in duration. So they're extremely close to their host star, and as a result, they're extremely hot. And so, those hot Jupiters, those so-called hot Jupiters, represent the first objects, the first exoplanets to be discovered around a main sequence star, and are still one of the most ubiquitous types of planet discovered because of the ease with which they can be found. And so for those planets, we're not seeing a rocky, we're not seeing a rocky object. So we can't ask geological questions in the way we ask geological questions of Earth. But there is still, there are still interesting questions that can be asked. And so some of our research has actually been to develop models to investigate those planets, because they're what we have data from. Those planets have constraints on, oxygen abundances in their atmosphere. And carbon abundances. And so we can think about what's the oxygen to carbon ratio in this giant planet atmosphere, and what does that tell us about how it formed, for example, or where it formed in its protoplanetary disk. And so I guess some of the work we've done is actually to sort of step away from rocky planets, except that the data we've got right now is for some giant planets, and just think about what kind of fun planet formation questions can we ask in that context? And so we built some atmospheric models to describe the chemistry of hot giant planet atmospheres and try and relate that to understanding their bulk composition. And then from that, comment on their formation history. So that's kind of one route, which I guess takes us quite far away from, normal actual geology in any sense. But it speaks ultimately to processes that are relevant for understanding solar system planets as well. Like, how do you form a giant planet? And what's the impact of a giant planet forming on, the architecture of the planetary system more broadly. For lower mass planets, there's less information, certainly on the atmospheric side. So typically what's known is at best their mass and their radius, such that you get a constraint on their bulk composition or their average density, which points to their bulk composition kind of crudely, albeit in a non-unique way. And there, obviously, that gives you rather little data to play with. We wouldn't, there wouldn't be very many geology departments if all we were trying to do was model Earth's average density of, 5 grams per centimeter cubed or something. But excuse me, what, the kind of things we can ask there are, so one key way we can sort of recover some information that allows us to start kind of doing some of the things we know how to do as geologists is by linking the planet to its host star. So realizing is maybe the wrong word, but employing the same sort of hypothesis that we do in the solar system, which is that, the sun is the majority of mass in the system. If we know the composition of the sun, we basically know the composition of all stuff that was present to make planets out of, and that the planets probably reflect, to a first order, that same composition. They're missing particular elements, like, mercifully, we've not got as much hydrogen as the sun and helium, et cetera, but, for good, honest rock forming elements, they're probably present in the Earth at roughly the same abundance they're present in the sun. And so that kind of, that classic chondritic hypothesis, which allows us to construct models of Earth's own composition, we can apply that to exoplanets as well. And now you quickly go from a planet which is just essentially an opaque blob about which only an average density, at best, to something which in principle, you maybe have a rough idea of the composition of its mantle, and therefore its mineralogy. And so maybe even the mineralogy and composition of the crust of the object. And that very quickly allows you to start thinking about, the kind of atmospheres that might form, and things like that. And I would say there's also kind of a separate role to be played for geologists in this context, which is a bit different to what we used to perhaps. But, if there are, these tens or down the line, maybe hundreds of rocky exoplanets that could be looked at, that we could invest, a lot of telescope time in looking at, a decision needs to be made probably about which ones to focus on. And maybe, the decision is made by which ones we can get the best observations from, and that might make the decision for us. But there might also be a case for, focusing observations on those which are going to offer the best opportunity to see some particular process. And obviously the concept of like a habitable zone and a planet lying at a distance from its star where it may have liquid water at its surface is, that's a model-based decision making tool, which is saying if you want to look at a planet that's got the best chance of having liquid water and kind of implicitly maybe life, then you're going to apply this habitable zone model and you're going to look at this subset of planets. And geology has a role in underpinning models like habitable zones, founded as it is on kind of climate modeling and the rock cycle and the carbon cycle, but maybe also for informing us what like an abiotic world would look like. What would an Earth-like planet look like in a habitable zone that has just done volcanic degassing, kind of without life having got in the way. So I think there's like a role to be played in kind of scoping out what we might want to focus telescope time on as well.
Yeah. That's so cool.
I had a follow-on I wanted to ask about that, Ollie. So I think what we're seeing here is this clearly the distinction between geologist and astronomer when working on exoplanetary science is a bit grey, it's a bit blurred. But I think it's probably fair to say that the work so far has been dominated by people who would have considered themselves astronomers and have been trained as such. How do you think that might change, if at all, in the next, let's say, 10 or 20 years? Do you have a grand plan or a vision for how geologists might become more and more involved?
Yeah, I think that's a really good question. I think, like, as geologists, we want an observation to explain, which I think is like the right way to pursue science, rather than just sort of doing random calculations, just kind of throwing calculations into the ether about what planets might be doing. It's nice to be trying to explain something that nature's done. And certainly at the moment, there's not much to be explained about certainly rocky, truly terrestrial type planets. But I think, that will change. And certainly there are some questions, I think there are some questions, classic questions in the earth sciences that are really pretty difficult to answer just studying Earth. So, for example, I guess Earth has probably spent some of its life as a magma ocean, probably a relatively limited bit of its life, but probably some of it. And to reconstruct the processes that happened in that, handful of million years, 4.5 billion years ago, which almost by definition has been destroyed by subsequent, geological evolution of the planet. That's really challenging to reconstruct that. But what exoplanets offer us are planets that will be trapped as perpetual magma oceans, either because they're so close to their host star that the irradiation from the star is enough to kind of keep its surface molten, or they have like a thick envelope of hydrogen and water on top of them, and that's kind of a thick kind of greenhouse blanket that keeps them molten as well. But in any case, we're looking or have already discovered objects which will be permanent magma oceans, and so the regime might be a little bit different to Earth age 10 million years, but it's a natural laboratory for investigating magma ocean processes, which could in principle, with improved atmospheric observations of those kind of objects, be a window into Earth's own history. So I guess that's kind of one thing, and again it requires technological development such that we actually get those observations and move to being able to investigate those objects through the chemistry of the atmosphere. And I guess the other thing, and the other thing is then, that's kind of the hot end of the spectrum. The other would be when we start making observations of temperate exoplanets. So I guess that we've already spoken about the, silicate weathering and the carbon cycle, and this idea of how Earth regulates its temperature by when it gets hotter. We do weathering of rocks more quickly, which draws carbon out of the atmosphere and restores the equilibrium, and the Earth doesn't get too hot because we reduce the greenhouse gas content of the atmosphere. That's kind of like a hypothesis, I suppose, probably a widely held hypothesis for how Earth has stabilized its climate, but it's one we can in principle test by looking at exoplanets, because you've got all these planets at slightly different locations with respect to their host star. You could look at their atmospheres and see, is there a correlation between the partial pressure of CO2 in their atmospheres and the distance and the amount of radiation they're receiving from their star? There's specific predictions that, theories kind of at the heart of understanding Earth's own history make. And, we can test that with exoplanets in principle. So I feel they're important kind of bits of Earth sciences that in a way need to be solved by studying exoplanets, but at the same time they're models which are calibrated on observations of Earth. So I think there's like a strong dialogue there.
This might be a good point to mention. When I was having a little Google stalk, I guess, before recording this podcast, I came across an article that you wrote, I think it was last year, about why geosciences and exoplanet science need each other. So this was in Elements, I think. So we can pop a link in the episode description, because that's probably a great article that, you know, explains these important links and the complementary parts of them. So
yeah. But I think, you know, at a fundamental level, though, I think it's fascinating that we can make these, you know, inferences about what the composition and sort of structures of different exo solar systems are like, based on sort of the data that we have at the moment and what you've been looking at. Do we have a sense then that there is a much sort of bigger diversity of compositions and architectures out there relative to, you know, what we see in our solar system? Are we quite unique in what we see in terms of an ultramafic mantle and a felsic crust, or is that generally what we're going to expect to find everywhere else?
Yeah, I think there's going to be some things which are, you know, really universal, like, you know, basalts are probably pretty common in the universe, but there is, like, if we just kind of I guess naively, or if we just kind of map stellar composition to planet composition, then although basalts might be common, there's definitely going to be planets that have, you know, really distinctly different mineralogies from Earth's own mantle, and that's going to be, you know, that's really interesting because you know, the mineralogy of the mantle affects, you know, its water storage capacity, its thermal evolution, its viscosity, you know, how easily it melts, the composition of the melts you get, yeah, all those kind of things, probably tons of other stuff I've forgotten. So, you know, yeah, it'll be fascinating to look at those planets and see, again, maybe through their atmospheres, whether, you know, they've done something different compared to Earth. So there definitely is a wider parameter space, even in the context of, like, you've got a one Earth mass planet. Even that could be a very different thing throughout these different planetary systems. And then there's the architecture, the wider architecture of the planetary system. And that's, of course, something we also know about. And in a sense, maybe is the kind of, you know, is almost the first thing, you know, is, you know, a detection of a planet is made. And sometimes if there are multiple planets, I guess you see multiple planets and you know their different periods and therefore how far they are from the star and maybe their relative radii and masses eventually. And so there's the opportunity to do kind of comparative planetology, but in an exoplanet context. So, you know, whereas we might compare Earth to Venus and to Mars and try and understand, you know, why Earth looks the way it does and Mars is smaller and has a slightly different composition mantle, and Venus is, you know, roughly the same size, but, you know, has this divergent climatic history. You know, we can maybe begin to play, you know, kind of ask similar questions of exoplanetary systems as well. Like, you know, what are there differences in finding an Earth mass planet with a giant planet kind of very close to it compared to just an Earth mass planet on its own? And we can already, you know, astronomers have already sort of started asking questions like that, certainly in relation to giant planets and giant planet occurrence rates, and, you know, what are the consequences of having taken a Jupiter and seemingly moved it right up next to the star? Does that just kind of knock everyone else out of the system on the way? You know, so that's the kind of an extreme example, but we do have the opportunity to kind of, you know, ask these kind of hypotheticals, like what would have happened if Jupiter was in the place of Mars or even closer to Earth? How would that have affected, you know, the inner small planets? You know, we see that being played out in the galaxy, and so it's going to be fascinating to investigate that further.
This is probably quite a broad question. What I guess when you're studying Earth and you're used to the structure of Earth, the geology and geochemistry of Earth, what the Earth's atmosphere is like, when you then started studying other bodies, what was the most surprising case that you had, you know, that really made you go, what on earth, how has this happened? That's probably quite a broad question to ask, but, you know, is there a point where you went, wow, okay, I've really strayed quite far from Earth now?
I think that, I think the planets that are kind of, that are sort of most exciting to me are, yeah, the ones for which we don't have analogs are in the solar system. And I think the really interesting bit of kind of parameter space that the solar system planets don't occupy is that mass range between Earth and Uranus and Neptune. And the question of, like, to what extent are they just an inflated Earth, with ultimately an incredibly tenuous atmosphere, and a system which is basically just loads of rock, versus kind of a shrunken version of Uranus and Neptune, where you have a very thick, gaseous envelope, and the rocky there is deeply buried and, at high pressure and high temperature. I think that's really, that's a really exciting, I think that's a really exciting regime, because it's kind of, where are the limits of geology in a way? And maybe on the way there, what you have are planets that have, extremely thick water oceans, for example. What happens if Earth had 10 times the mass of water at its surface? Could it still regulate its climate? Could plate tectonics still happen? These are, we don't really know the answers to these questions. We can kind of model them based upon, how we think water rock reactions occur, again, informed by, terrestrial geology and geochemistry. But these are going to be amazing objects to study over the coming decades, and sort of, and fill in that gap.
Yeah, I guess I was going to ask then, I guess, is that the next step, I suppose, is taking some of these inferred compositions and, hitting up some experimental petrology labs and sort of start to flesh out some of these ideas and things?
Yeah, I think there's definitely really exciting scope for, motivating new experimental work. And I think, it remains, and it has been extremely hard even to access the pressure and temperature conditions inside the Earth. The deep mantle and the composition of the core, those are extremely challenging experiments, even for a planet as small as the Earth. I mean, if you double its mass, then it poses really interesting questions, like how, what's its thermal history? What's the mineralogy at a mantle that's going to twice the pressure of Earth's mantle? What is that mineralogy? What is its viscosity? How does mantle convection work? Is the upper mantle of the planet completely, chemically decoupled from the deepest part of the planet, because of differences in viscosity and things like that? I'm not, I don't think we've got all the kind of experimental data and, therefore thermodynamic models that we need to be able to answer those questions, and it's that at the heart of understanding the dynamics, and evolution of large rocky planets. So I think it's super exciting in that it kind of motivates, more study, both theoretical and experimental.
Yeah, sounds like a tremendously exciting field to be in.
Follow on from that then, let's say we had a viewer in the audience who was in their undergraduate studying geosciences and who really fancied getting into some exoplanetary research and work. What would you, if you had a few tips for them, what would they be, Oli?
Yeah, I still think I certainly would say that I feel like the disciplines, and certainly different disciplines in the kind of UK science context, that whilst we can be intellectually kind of sort of fluid between these different areas, the realities of being able to do research and be, resourced to do it, create sort of barriers or kind of divisions between research activities, which are a little bit artificial. And what I really am saying in a kind of oblique way is that obviously research funding councils have remits which are discrete and non-overlapping, and that does kind of make it a little bit tricky to kind of just move between areas. That said, I think for someone doing geoscience, I would just encourage them to do the geoscience that they're most passionate about, whether it be kind of low temperature geoscience, or high temperature geoscience, or even like the biosciences, whatever kind of field of the geosciences you happen to find yourself in, just pursue that. and just kind of keep an eye on what's going on in the kind of planetary science or exoplanetary science domain. And I kind of see, I feel like it's a complete sort of umbrella discipline, that there's opportunity for all geoscientists, I think pretty much all geoscientists to contribute to. And certainly in Cambridge, we're just starting this initiative, kind of a planetary science life in the universe initiative that kind of really tries to bring in, biology, astrophysics, earth sciences, chemistry, organic chemistry, like origin of life chemistry, and kind of bring it all together to ask questions, whether it be of Earth's past, solar system sciences, like Venus's past, Venus's present, and exoplanets as well, and just kind of really recognize the continuum between all of these different disciplines and their ability to contribute to each other. So I guess what I'm saying is, like, if you're a geoscientist and loving doing geoscience, researching it, studying the northern rift zone of Iceland, which everyone should be doing, then just go for it. And like, if you're interested in the kind of astro side of it and the planetary side, then I'm certain there'll be an opportunity, or there are already and will continue to be opportunities to kind of apply that expertise that you've kind of honed on Earth observation and analysis and theory to the exoplanet or planetary science context, and that you can do both. I think that's the kind of cool thing. You don't have to give up on studying Earth. You can do research grounded in observations of Earth, and you can do, you can apply some of that insight to particular types of exoplanetary questions as well. So yeah, you can have your cake and eat it. I think that's what I'm saying.
Well, I think that sounds like a good message to maybe wrap up on. I mean, that's a good positive message.
Do we do final question though, John?
Indeed, yes. We have one last question for you that we ask all our guests that come on. So basically, if you hadn't gone down the route of becoming a research scientist, what outside of academia do you think you might have done?
Maybe there's an answer I'll give on air to that, and maybe there's then an answer which I can then off air answer. I think the on air answer is I'm really interested in politics, and I guess by politics what I mean is the way in which groups of people make decisions, and the structures that we create to help us make decisions. Sometimes bad decisions, maybe often bad decisions, but I find that really, really fascinating. So I feel like either I would have just tried to become a political scientist, which I guess effectively I would have just tried to do the same job, but not knowing less about rocks and more about political science and history, or maybe I would have tried to go and I don't think I've got any hope in politics, but sort of go and work, somewhere in the kind of, public sector where, decisions are being made and policy on issues and stuff, because I find just the way in which decisions are made really fascinating, and continue to do so. So my kind of hobby is, reading about politics and stuff like that.
Yeah. Well, sounds good. Yeah, I mean, sounds like it's good, isn't it? I think the theme that we've seen a lot throughout the episodes, isn't it, is people wanting to stay in, socially active roles, making a difference and stuff like that. I think that's definitely a very noble pursuit. Oli, thank you very much for coming on. That was an absolutely fascinating conversation. It sounds like such an exciting field to be in. We'll drop some links in the episode description to a few of your papers and stuff, as Marissa said, for anyone in the audience wants to read a bit more about this. But yeah, I guess all that remains for me to say is thank you once again, and thank you all to watching this week's episode. Don't forget all the social medias if you want to like, comment, subscribe, etc. will be populating the screen right now. But yeah, until next time, we'll see you later.
Thanks so much for having me.
Bye everyone.